On tip, and this is a PCB seed. If you're someone who works with digital circuits and this is your first time dealing with RF PCBs, you'll probably have a thought like, guess, isn't this just a wire? When I used to design digital boards, I just connected the power, ground, and signal lines. As long as it worked, that was good enough. But when I started working with RF, suddenly the power was gone, there were reflections, and weirdly enough, it started radiating. Welcome to the world of RF, where simply connecting the wires is just the beginning. Digital PCBs and RF PCBs might both look like you're just designing a board, but the things you think about are completely different. A digital engineer asks, does this thing work? Is the logic correct? Is it consistently meeting requirements? Can zeros and ones be reliably recognized? But an RF engineer is thinking about whether the impedance is matched, how much reflection there is, and whether the power is actually being delivered. Is the efficiency high or not? It's still just a PCB, but the focus is completely different. If you had to sum it up in one sentence, it would be this. The core issue for digital PCBs is as long as it works, the basic task is done. But for RF PCBs, the core issue is that even if it works, that doesn't mean it works well. You might lose half the transmission power, or the receiving sensitivity could drop beyond acceptable limits. In RF, just working is only a passing grade. Matching it beautifully is what makes it excellent. Digital is about logical relationships, while RF is about physical relationships. This is where a lot of people have a real turning point in their understanding. In the digital world, it's just a wire carrying voltage from point A to point B over time. And that's basically it. But in the RF world, it's no longer just an ordinary wire, it's a transmission line. Electromagnetic waves travel along it. It has impedance, phase, loss, and reflection. So in the RF world, every single wire really needs to be carefully designed. Details matter. So, where do RF problems actually come from? Usually, it starts like this. Step one, the impedance of the transmission line doesn't match the load impedance. Then, step two, the signal starts to reflect. Part of the energy bounces back, and then comes step three, a standing wave forms, also known as the VSW point. Step four, the actual power delivered to the load decreases. Finally, problems start to show up. Efficiency drops and heat increases, radiation increases, and performance becomes unstable. That's why RF engineers spend every day doing one thing, making sure energy is delivered cleanly and efficiently to its destination. At the end of the day, RF is all about one thing, matching. If watching this particular video happens to be the very first time that you are actually realizing this fact, RF and digital PCBs are completely different ways of thinking. Then, congratulations, you've already taken the most important first step. Next, we'll break down this series, and in the next episode, we'll answer a classic question. Why are RF traces 50 ohms? And actually, 50 ohms isn't even a resistor at all. If you don't want to be afraid of RF anymore, make sure to follow. We'll also cover microstrip, stripe line, and coplanar waveguide in the future. We'll also talk about S11, return loss, VSWR, Smith charts, and what real RF PCBs involve. Thank you for watching.